Okay, so we're going to pick up from where we left off yesterday. Built up a lot of hype, but it didn't go anywhere because it didn't even start any examples. But just recall that the limit as x approaches a of f of x equals L means for all epsilon greater than 0, there exists a delta greater than 0 such that if your distance between x and a is less than delta, possibly never being equal, your x does not necessarily have to be equal to a, then the distance between f of x and L would be less than epsilon. So if we make our x values close together by this distance specifically, our y values will be close together by that distance specifically. So someone will give you the tolerance, epsilon, and they want to say, okay, I want to make sure the y values are at least this close. And you are going to tell them what the delta must be so that the x values need to be close enough by that distance to give them that tolerance. Okay? And that's what getting close means in a more specific way, because now you can actually put numbers into it. Okay? So it's not just a matter of vagueness anymore. So that was the definition. That should be memorized, burned into your brain. It's one of those things. We had some examples which we're going to work through. I believe I asked you to prove, which there are many other ways I could say that, so maybe I should just write down. If the moon strikes, I might say something different. Or show, or use the epsilon-delta definition, or use the definition of a limit. Right. So there's a difference if I ask you to calculate a limit, compute a limit, versus prove that this is the limit, show that this is the limit. Use the epsilon-delta definition to say that this is the limit. And we had 3 examples. Limit as x approaches for some random linear function. 4 of 3x minus 7 equals 5. B, the limit as x approaches 3 over 2 of 4x squared minus 9 over 2x minus 3 equals 6. And C, that the limit as x approaches 2 of x squared is actually 4. So let me start you off with the first one, the easiest one. And so now you can kind of see how you'd be expected to write these down. So first you need to identify who is who. So when you're saying limit as x approaches 4, 3x minus 7 equals 5, you should first recognize that the 4 here is your a, and this guy here is your f of x, of course, and this guy here is your L in that definition. So you should realize you need to show given any epsilon greater than 0, you can find delta greater than 0. That's the main part. That's you solving the problem. You need to be able to find that delta so that if your x minus 4 in absolute values is less than delta, perhaps x is never reaching 4, then your f of x minus your L in absolute values must be less than that epsilon. Right? So to apply this definition, you're literally picking out the pieces, and ultimately, when you sort of substitute the specific problem into the definition, that ends up being what you have to show, and your work is here. That's where all the work is. So pretty much you're going to tell them, pick your delta to be this, and this is going to work out, and you need to show that it's going to work out. That's the whole point. Okay. So here's how you would start it. Let epsilon be greater than 0. That's it. Okay, so that's how it starts. Choose delta equals, you don't know yet. Then, if x minus 4 is less than delta, we will have that our 3x minus 7 minus 5. Okay, so here's the real thing now. Here's how you're going to find that delta. You want to use this fact to prove that this must be less than epsilon. So when you get to this point, you're going to kind of go to the side. It's usually not done in the problem itself. It's usually done as rough work somewhere. You're going to go to the side and you're going to try to make sure that that's less than epsilon. Okay? So you go here, and this is scratch work here. So okay, so we have 3x minus 7 minus 5. I want that to be less than epsilon. So we can start simplifying. What is that? 3x minus 7 minus 5 is what? 3x minus 12. Can you simplify that anymore?
Take a 3 out.
Can factor out a 3. And remember, the absolute value of a product is the product of the absolute values. So technically this is 3 in absolute values times x minus 4 in absolute values, or just 3x minus 4, right? Now the fact that you have the x minus 4, this is something you want. You want to be able to give a restriction on that guy, because that's required by the definition, in order to force it to be less than epsilon, right? So now what you can do is you actually force it. So you set this guy 3x minus 4 less than epsilon, and that would mean that your x minus 4 in absolute values would have to be less than epsilon over 3, right? So you do this on scratch work, and then you come over here and say, choose this to be epsilon over 3. Right? So you pretend you knew that all along, you just looked at the problem and you knew what the answer was. No, in reality you went on scratch work and you solved for what it had to be. Okay? And so now what's going to happen? Now we come back to the problem. So here's how the solution is going to look like. Let epsilon be greater than 0. So give me any epsilon greater than 0 that you want. Choose your delta to be epsilon over 3. So if someone tells you, I consider close to be 30 units away. Okay, choose delta to be 10. Right? Or I want epsilon to close to mean 1 unit away. Okay, choose delta to be 0.33. Right? Whatever they tell me, I'm going to respond with a tolerance on the x values. Right? Give me this, give me whatever tolerance you want, make that the tolerance for x's, and here's what's going to happen. Provided that this is less than that, we're going to have this guy equals 3x minus 12, and that's going to be equal to 3 times x minus 4. However, we know about that x minus 4. That is here. Now it turns out that that should be less than, of course here's a 3. My x minus 4 is less than delta, which is epsilon over 3. And so I can literally replace this expression with epsilon over 3, and I would get something less than. And so now obviously there's a simplification that can happen. The 3's would cancel. And so epsilon would be the answer. So in other words, give me any tolerance you want, any positive distance that you require for the y values to be close. Choose this to be your delta, epsilon over 3. Whatever value you give me, I'm going to just divide that by 3. And force that restriction on the distance between the x values and 4. Once my x values are within a third of epsilon away from 4, this computation shows that the f of x minus L in absolute values will be less than epsilon. And that actually completes the proof, that's it. So you put a box and you shade it. Back in the day, people used to put QED, which was a Latin, it was the abbreviation for a Latin phrase that meant as was to be demonstrated, but they've since gone away from that. Modern textbooks would use a shaded square to indicate the end of a proof. But that is the proof. So this would be a full answer here to the question, prove that this limit, this equation here is true. Right? Let epsilon be greater than 0, choose your delta as epsilon over 3. Then, if x minus 4 in absolute value is less than delta, my f of x minus L is ultimately, by this computation, less than epsilon. And so what you realize for this process is there's kind of even a template that you can do with these processes here. And I don't want to be too misleading. That's not something in general. But with the kind of problems we'll ask you in Calc 1, it's pretty much going to be straightforward like this most of the time. Problem C is going to have a little bit of sketchiness in it, but we'll deal with that when we get to it. So in other words, by the way, before I erase this and write down, any questions on what happened? Questions anywhere? Do you understand how I use the definition? How what I wrote down fulfills this definition?
Yeah. So over there, when you get the 3 times the absolute value of x minus 4, you put the less than 3 times epsilon over 3 because that's what you found over there, right?
Because yes, and because I literally I replaced this with that, and this is bigger than that.
Okay.
So it's kind of like you're saying, if you know that 1 is less than 2, it's also true that 1 must be less than 3 because 3 is bigger than 2. So if you swap this out, you can keep the inequality sign. So that's kind of what I did. I swapped out the x minus 4 with that expression, but this expression here is bigger, so that allows me to say this is bigger. But that simplifies to epsilon, which it should, because that's what the definition says I should have. Yeah. So, for all epsilon greater than 0, meaning you have no control over this should be anything, there exists a delta greater than 0. This means you need to find one, show that there exists something. So you need to specifically state who you're going to pick. And in this example, picking that is the right thing to pick. Okay, so you can show that such a thing exists. You need to tell them what it is, such that if the difference in your x values is less than that number, the difference in your y values will be less than epsilon. And so that's what that shows. And so essentially with a problem like this, so what you can even think of is a template for these problems. So if someone asks you to prove a limit exists, and you're in Calc 1, you're pretty much going to regurgitate this exact argument, where you're going to fill in some details with calculations. Right, so if someone says prove that limit as x approaches a of f of x equals L, you can write down the proof. It's just me writing short for proof, because I'm too lazy to write down the 3 extra letters. You would say let epsilon be greater than 0. Some people like to say let epsilon greater than 0 be given, but it doesn't matter. You can just say let epsilon be greater than 0. Choose delta equals, and this is something you have to fill in. That's the template. You're going to start, let epsilon greater than 0, choose delta equals blank, right? You need to figure out that blank in much in the same way that I did it down here, right? Do the calculations, force it to be less than epsilon, and then figure out what you need the x minus a to be less than for that to work, right? And you're going to put the answer there. And then you're going to say, then, if x minus a is less than delta, we have f of x minus L equals, and here you're going to do a bunch of calculations. Calculations involving substituting x minus a with delta. And ultimately, at the end of this line, you need to end up with less than epsilon. And then you're going to put a box here, and you're going to shade it. The solution to all these problems will look exactly like that. That's the template. Right? So that's kind of a form you need to fill in. Basically, you memorize this script. I mean, it's not very sexy to say that, but we're not in a proofs class, so I don't expect you guys to be able to like wing it with the language here. So you can use this script for a Calc 1 case, it's fine. So yeah, you're pretty much filling in these 2 spots right here. Right? And the calculations that you do here are very similar to the calculations that you're going to show here, except there you kind of force it to be less than epsilon, and here you're kind of showing that it's less than epsilon based on what was chosen then. Right? So you kind of start the proof with this expression, pretending you knew what it was all along, but you really didn't. You did some scratch work. And then you show that it's true here. And that is proving that the limit as x approaches a of f of x equals L. Now it turns out you can actually disprove this. We're not going to do that in Calc 1. That's kind of, because then I'd have to talk about logical statements and negating a logical statement. You have to prove the negation, and we don't want to get into it. But you can basically show that there are times when this just won't work no matter what you try to force it to do. It's just not going to work out. But here, I'm going to ask you to prove something that works out, and that's going to be the script. Okay. Now, given that, try B. Give you guys a few minutes there. Give about 3 minutes. Try to work out B and fit it on this script. Okay, I'll give you guys about another minute. Okay, what do you guys think delta should be equal to? Yeah?
Epsilon over 2.
You think epsilon over 2? Okay. Okay, so like I said, it's a template. You can literally just fill everything in here. So now we have 3 over 2. This is the function 4x squared minus 9 over 2x minus 3 equals, what? Didn't say what was equal to. What did I say it was equal to? 6? And he said epsilon over 2 should work. And how did you come by that? What calculations did you do?
You can factor the f of x, and that leaves you with 2x plus 3 minus 6 and the absolute value.
Okay. So this is your f of x minus L. And so you start simplifying this. Okay, so the top factors, it's the difference of squares, 2x minus 3, 2x plus 3. Of course, that cancels, so we end up with 2x plus 3 minus 6 in absolute values. Well, that's just 2x minus 3 in absolute values. You could factor out a 2. And there you have your x minus 3 over 2, and 3 over 2 is your a, so now you have x minus a in absolute values, so hey, that's what we want. So at this point you're like, okay, cool, force that to be less than epsilon, and that results in you being able to say that you want your x minus 3 over 2 to be less than epsilon over 2 by just dividing both sides by 2. So yeah, to prove this, let epsilon be greater than 0, choose your delta to be this. Then, if your x minus 3 over 2 is less than that delta, we would have this equals that, which is equal to that, which is equal to that, which is equal to that, which is less than, this is less than 2 times epsilon over 2, which ends up being less than your epsilon, or equal epsilon. Yeah, that's it. Epsilon over 2. Good. Epsilon over 2 worked for this particular problem. So whatever tolerance someone gave you, the tolerance for the x values would just be half of that. I want to be within 1 unit close for the y values. Okay, make sure the x values are half a unit close. Okay, let's actually look at C. Now, if you try to work on C, we're going to do it together. You're going to see an issue happening here. Section two. Okay. So you kind of know what you want to happen here. So you start by, okay, you let epsilon greater than 0, choose delta equals blah, you're going to figure that out later, and then you say, okay, then if x minus 2 in absolute values is less than delta, perhaps not equal to delta, we have, so now you're going to say, okay, f of x minus the L. And so now ultimately you want to simplify that into something where you can substitute x minus 2 is less than this delta value and ultimately end up with something that's less than epsilon. So immediately you might think, okay, I can factor that. Definitely I can get the x minus 2 by factoring this. So that's going to be x plus 2 times x minus 2. So that's just x plus 2 times x minus 2. Now, this is a problem here, because now, I'm going to show you why it's a problem. If you force this to be less than epsilon, you would get that your x minus 2 is less than epsilon over this. And the fact that there is an x here in your approximation is a problem. You can't put a restriction on the x in terms of the x itself. Computationally, that is problematic. So now it's kind of like, someone gives you a tolerance, there's too much uncertainty, right? You can't say, well, take that tolerance and divide by this variable, and now you need to figure out what the right value of that variable is in order to make sure this works. That's not certain enough. So the x being there is an issue. So now somehow, you need to be able to figure out, how can I replace this thing with something that is definite? It's a value that I don't have to have the reader guessing as to what's going to work, right? Because we do want some certainty here, no ambiguity. Give me the epsilon, choose delta to be this, there's no ambiguity in that answer. So this one ends up with an issue, and this could, I should also take the point to remind you that yesterday I mentioned, recall, your delta depends on epsilon, not x, right? So it can be a function of epsilon, but being a function of another variable is problematic, because that means you would require more information than just the epsilon which you are given, and that's problematic for the definition of the limit to hold, right? There's ambiguity there. So the fact that there's an x here is an issue. So now I have to figure out how to do that. And here's the conventional way to deal with this thing. You're going to insert some definiteness to it. So, how to deal with this issue? So first, assert some value for delta. So you can say something like, usually it's used to be 1. So you can say something like, assume delta is going to be less than or equal to 1, okay? So you're giving yourself a restriction, you're giving yourself some leeway. There's too much ambiguity. Okay, let's pretend that 1 is the farthest away I will allow you to move the x values, but now we want to refine this approximation, right? So I just threw an approximation out there. Okay, make sure the x's are 1 unit away, okay? And what we're going to do now is try to account for that. So starting with a 1 unit window as a maximum, now we're going to try to refine that idea. Okay, so once you do that, now refine to make sure that your x minus a less than delta works. So in other words, what you would now have, to assume that your x minus a should be less than delta, this would mean, if your delta is 1 or less, this means now that your x minus the a is definitely less than 1, right? Because that's the maximum leeway we're allowing to give. So whatever that expression is, it's definitely less than 1. Now what we can do is we can start working on the absolute value, this expression. Ultimately, remember what we want to do, we want to get rid of the expression x plus 2. So ultimately I want to be able to say x plus 2 is less than some number. But what does this mean, absolute value less than 1? How can we start to break that down? If your absolute value is less than k, this means remember how absolute values work? What does that mean? Almost. There's an expression that it means. How do you simplify that? In other words, getting rid of the absolute value would mean what statement? Do you know? You're smiling. Do you know what you'd replace it with? That expression means that. You should know that. That's way back in algebra. In general, absolute value less than a constant means your x is between the positive and negative value of that constant. So we have that. In other words, I can add 2 to both sides, and I know that my x value must be between 1 and 3 for this to hold. I don't necessarily care about the x value by itself, I care about x plus 2. So now what I'm going to do is I'm going to add 2 to everywhere. Add 2 to this, x plus 2, add 2 to this, 5. In other words, assuming this as the maximum leeway I'm allowing for x minus 2, that would imply that x plus 2 must be less than 5 in absolute values. So putting a bound on my delta allows me to put a bound on the x plus 2. So now what we can do is we can go over here and apply that. So now I can go back here and apply that. So it means if I replace x plus 2 with 5, I would have this. And so now, epsilon over 5 is the guy to beat. So your delta you have a choice of delta. This is the maximum you'll allow it to go, but it could be as small as this guy. It depends on how big your epsilon is given, right? So if someone gives you an epsilon that's less than 5, you would use this approximation. If someone gives you an epsilon that's greater than 5, like say 15, then this one will automatically work. And so here's how you actually write down this one. There's a slight modification in the template. Well, it's not modification, it's just what you fill in is stated differently. Because here in your bound you have an x, you have to get rid of that somehow. So you use some sort of maximum allowable tolerance to get rid of that. So you would say the following. Let epsilon be greater than 0. Choose delta equals, and here's how you'd write this down. take the minimum, the smaller of these two values. Compare 1 to epsilon over 5, and whoever is smaller, pick that guy. In other words, once your epsilon is larger than 5, choose 1. If your epsilon given is less than 5, choose epsilon divided by 5. So now you have a choice of deltas, but they're very specific choices. Either you're going to pick 1, or you're going to pick epsilon over 5. Pick the smallest one. That will ensure that your inequality is going to hold. And so then you'll say, then, if x minus 2 is less than delta, we have, what was my f of x? F of x minus L equals x squared minus 4 equals x plus 2 times x minus 2. Now this is going to be less than, once I chose a maximum for delta, this guy is less than 5. We've discovered that here. So now once I replace this guy with epsilon over 5, that gives me the epsilon in the end. And that's the hardest kind of problem you'll get here in this class. So you just want to make sure that whatever epsilon someone gives you, you can choose a very specific delta that when applied to f of x minus L in absolute values, you'll end up with something less than epsilon. That thing that you bounded by cannot involve x, because that means there's ambiguity here. So whenever that happens, you can pretty much just give yourself a maximum window that you're willing to adhere by. Usually people pick 1 just because. It's a nice number to work with. And assuming that that's the maximum window, this is forced on you, which ultimately allows you to solve for any other x by expanding the absolute value. So you can essentially get to any expression, or most expressions that you would see that would have x in them. That allows you to bound this guy by a number. And then pretty much you take your delta to be the best one that works in the given context. So depending on the choice, you would choose one or the other, and then that will make everything work out. Any questions on this one? So that's what the solution to this one would look like. So in the remaining time, I just want to tell you about some other definitions that can apply here. So now that we've redefined the limit, it turns out a lot of other things, the way we've been thinking about them, can also be redefined. So for example, continuity. Remember, the definition of continuity involves a limit equation. So you can actually state this in a different way. You can say f of x is continuous at x equals a if for all epsilon greater than 0, there exists a delta greater than 0 such that if your x minus a is less than delta, then this expression, f of x minus f of a, will be less than epsilon. Because remember what continuity requires is that the limit as x approaches a of the function is specifically f of a. So simply replace the L in the limit definition with f of a, and now you have the continuity definition in the same way. So pretty much if you want to prove something is continuous, what you're going to do is you're going to evaluate the f of x at the point, and whatever answer you get, you put that here in the place of L, and then you can do the proof after that. And if that works out, you can say it's continuous at that point. We also can talk about, did I talk about, yeah, infinite limits. One way you can express this is the limit as x approaches a of f of x equals infinity means for all m's greater than 0, and I'm using uppercase M to denote that here m is going to represent a very large number, not a small tolerance, as you might assume epsilon is. For any large number, there exists a delta greater than 0 such that if your x gets very close to a by that delta, then your f of x will exceed that value n. So saying the limit as we approach a of f of x is infinity means no matter how large a number you give me, you say a cajillion. Eventually I can make my x close to a such that my function will actually pass that value. Any value you give me, my function will eventually be bigger than it, in other words. So you can think of that something like, if we look at, say, 1 over x squared, and we said that the limit as x approaches 0 of 1 over x squared, we know that's infinity. In other words, what we're saying is that, well, pick a value, right? Someone says 1,000, right? All I have to do is make sure my x gets this close to 0, and the y value will pass that. Someone says something bigger, 1,000,000. Well, all I have to do is make sure I get this close to 0, and eventually the y value will pass that, right? So no matter what number someone tells me, I can make my x get a little bit closer to 0 to make the y values pass that value. And if you can do that for any positive value someone gives you, infinity is the only thing that would make sense, because you will now show your y values will exceed any positive value. It has to be infinite. It has to go towards infinity. Similarly, to say that a limit is negative infinity means for all negative numbers, for all numbers less than 0 that you can give me, no matter how negative, there exists a delta greater than 0 such that if I let my x values get close enough to a by that delta, then my y values will actually be smaller than whatever negative value you give me. And that would mean that no matter what number you give me, eventually my y values will be lower than that number. It has to be negative infinity. Now, the first definition that I asked you guys, I told you guys to know about proving that a limit exists, blah, blah, blah. That one you have to know, and you'd have to apply as in the examples I did before. In Calc 1, I usually won't, I'm not going to ask you to prove either of these concepts via this method. right? So I'm never going to ask you to prove continuity via epsilon delta, or to prove something's infinite by epsilon delta, or to prove something's negative infinity by epsilon delta. But you should know these definitions. If on a quiz I ask you to state one, I expect you to know it, but I won't actually ask you to compute one. One of the 3 examples that I started the class with, though, that's fair game. I'll ask you to actually prove some limit exists and is a finite number via the definition. That's something you need to know. So that's definitely going to be on the next quiz, and it's definitely going to be on the first test, and it's definitely going to be on the final. So these definitions, I'm pretty much telling you just to be comprehensive. I'm never actually going to test you in applying these, but it's things you should know. And yeah, that's it. Tomorrow is a very great day. We were finally going to sort of leave our discussion of limits, and we're going to start to attack the rate problem. So not tomorrow, Friday. I'll see you guys on Friday. And if you have a quiz later today, good luck on that.